So, good evening, everyone. Welcome to the live session. Today, we'll be discussing practice problems from week 6 content. For a brief introduction, I'm Polumi, one of the TAs for the NPTEL Natural Language Processing course. So we'll wait for 5 minutes and we'll start at 7:05. Okay, so good evening, everyone. So let's get started with the first problem of the day. So today, the first problem is we need to say which of the following statements are true for this algorithm. So among the 4 possible options, you need to say which are the options that are correct. Please try the problem once. We'll discuss the solution in a couple of minutes. And in case you're able to solve, please post your answer in the chat. Okay, so only one of you have answered till now. So since there's a problem directly from the lecture, so I think more of you can try. So this is a question directly from the slides. So I think all of you can give it a try once and post your answer in the chat. We'll wait just for 1 more minute, and maybe in meanwhile, if you try, just Okay, I think we can start with discussing the solution. So, Vandana has said that the answer is 1 and 2. So, Vandana, would you like to say, like, how did you come to the solution? Any of your thoughts?
According to this question, I think one or two is correct because in the first statement it says each vertex in the graph will be selected by the height vector. So I think so in the Greek algorithm it it will be select the hash,
Okay.
and the second one is also correct. I think during the rotation of the always there is minimum MHD. I mean there is MHD. So
Does it always produce minimum spanning tree?
I think so. I'm not
Okay.
sure.
Okay. All right. So, anybody else would like to add into what Vandana said? Please feel free to unmute yourself and um, give in your thoughts. Okay, Guna Sundari has said it's 1 and 4. So how about you? Would you like to say why you think 1 and 4 would be correct?
It always produce the minimum spanning tree and produce the cycle also during iteration.
Okay, so you have mentioned 1 and 4 are correct according to you, right?
Yes.
So 2 and 4 would be incorrect as per what you're saying.
1 and 4 is correct.
Okay. Okay, so you're saying that it may or may not produce a minimum spanning tree at all times.
Yes.
Okay. Okay. How about option 3? Is there a possibility of creating a cycle at any point of the iteration? Okay. Okay. All right, then let's discuss the official solution once. So the answers are 1 and 4. To understand why that is the case, let's just briefly discuss what is the algorithm. So the first step of the algorithm consists of, so for each vertex in the graph, we follow a greedy strategy and we select the incoming edge for each such vertex which has the highest weight. Okay, so after this first step, what is so we get a modified graph with fewer number of edges, and in this graph we need to check whether it is a minimum spanning tree. If it is a minimum spanning tree, we got what we are looking for. If it is not, we further check if there's a cycle or not. If it is cycle, we need to further like identify the circle, contract the circle. We need to take for like additional steps to take into account if there's a cycle, and then further recalculate the weights and again go over the same steps until we come to the solution. So here what we saw is So here, what we saw is, so which of the options would be correct? So the first option is directly aligning with the first step of the algorithm. So option one is correct. Second option says that during the iteration, it always produces a minimum spanning tree. So that's not necessarily the case. It may or may not produce. So if it produces, well and good. If it does not, then there are further steps to the algorithm that we must follow. There's The third option was during the iteration of the algorithm, it never produces cycle. However, that is not necessarily the case. There is a chance that a cycle may appear after the first step of the algorithm. In which case, what we need to do, we need to identify the circle, contract it into a single vertex, and further go on with the iteration of the algorithm. So, option three would also be incorrect. So that leaves us with the first one being correct, these two being incorrect. So the fourth one is the running time of the algorithm is O into O of the order of E times V, where V is the set of nodes, E is the edges. So here, if we look at the first step, so what we are doing for each vertex, we need to find the incoming edge which has the highest weight. So for each vertex, we need to go over all the edges that are present, and we need to find the one which has the highest weight. This is a order E time algorithm, and that needs to be done for each vertex. So we get a order E times V running time for the algorithm. So that gives us 1 and 4 would be correct, 2 and 3 are incorrect. Does anybody have a doubt in this problem?
Ma'am, but in the solution you have written here during the iteration of the algorithm, it always produces MST. So according to this, option two can be correct.
So it so at each step, so if there's a cycle, so a cycle does not necessarily give you a minimum spanning tree, right? A cycle and minimum spanning tree cannot always be possible. So there is a case that whenever you're creating, so we'll also see a problem. So today we have a problem coming up where we'll do this algorithm. There, I think once we solve that, I think it would be more clearer. For now, you have to see. So what we are doing is, since at each step for each vertex, we are ensuring that. So what are the requirements for a minimum spanning tree? So the vertices that are there in the original graph and the reduced graph, the vertices has to be exactly the same. However, we select a subset of edges, okay, such that we get a spanning tree, right? So here, what we are ensuring is that, so for the what does the first step do for each vertex? Since we are selecting an edge, so all the vertices will have a corresponding edge. But if there's a cycle being produced, because of that, it would no longer be a spanning tree. So there, it's not always the case. Okay, so there are three conditions, right, for the creation of a spanning tree. The vertices should be the same. The number of edges should be equal to the number of vertices minus 1. And the third condition is there should not be a cycle. Okay, all the three conditions need to be mentioned. So after doing the first step, the first two conditions are maintained. The number of vertices are the same. Number of edges would be number of vertices minus 1. However, the third condition may or may not be maintained. If it is maintained, that if there is no cycle, then we have a minimum spanning tree. However, if there is a cycle, we need to uh, further iterate over the algorithm and see what we can do about it. Is it clear now?
Yes, ma'am.
Okay. So this is the second problem. So it is with respect to the dependency structure, which of the following is not a valid criteria for a syntactic relation between a head and a dependent in a construction. So this is also an easy problem that was discussed in the lecture videos. So just try the problem once and we'll discuss it. Okay, so let's discuss. So some of you have tried solving the problem. So let's hear from some of you. So Archana says that the answer is 2 and 4. Archana, would you like to unmute yourself and say, like, how did you come up to the solution? Yeah, go on.
According to the criteria of heads and dependents, the form of dependent depends on head. So, so the first option is true. The question here asks is the invalid criteria.
Okay, yeah. Okay, that's correct. Um, would anybody else like to add on to what Archana said? Okay, then let's discuss the official solution once. So before going on to the solution, let's just go over what are the different criteria that have been put. So these are the necessary criteria that have been established between the head and the dependent to in order to have a valid syntactic relation. First is the head determines the syntactic category of a construction. So here we have this sentence, right? He sent her a letter. So let's pick up a construction. Let's say a letter. Okay, so this is a construction over here where the head is letter and A is the dependent. Okay, so in this construction we see that the head, which is letter in this case, that is determining the syntactic category. So what would be the syntactic category? A letter is a noun phrase. And letter itself over here, letter is the noun, A is the determinant. Okay, so we see that the head is determining the syntactic category of the overall construction. And even head can replace the construction. So head is serving the predominant grammatical functionality of the construction, and instead of a letter we can simply write letter and we'll still have a valid construction. So that is the first criteria. Second one is the dependent D specifies age. So D specifies age means so D gives much more specific and more additional information about the head. So here again we see that the dependent, which is A in this case, it is specifying that we have a single letter. If that was absent, we would still have a noun phrase because the head letter itself is a noun. However, the dependent A is providing much more specific and additional information, which makes the construction much more fluent. The third is H is obligatory and D may be optional. So the head must be present. It is mandatory. However, the presence of D is optional. So again, it would be a reiteration, but so here we can omit A and simply keep letter, and that would justify this point in the this criteria. The fourth criteria is that H, the head, selects the dependent and determines whether D is obligatory. So it's completely dependent on the head of the construction, on what is the dependent that it is selecting, and also whether the dependent is a necessary part of the construction or not, whether it needs to be present or it can be omitted. The fifth criteria is the form of D dependence on age. So here form means the grammatical form. That again is like so the grammatical form of the dependent would be depends or is determined by the head. Okay, so we have the notion of grammatical agreement present. So this is what is further established by this criteria. The last one is the linear position of D is specified with reference to age. So here we see, so here this is again a construction, right? So if we see the word sent, it is the verb. Its dependence would be, we have the subject that is he. So he is a dependent. Sent is the head. Again, let's take her itself. So her is the indirect object. Okay. So in English, English follows a specific word order, so which is subject, verb, object. So if we have the subject over here, if we have the verb over here, the subject will be appearing on this side and the object to the other side. So that needs to be maintained at all times in English. So based on where the verb is appearing, so the linear position of the dependent, so if I consider the dependent to be subject, I know that it would be appearing on this side of the verb, whereas if the dependent that I'm currently considering is the direct object or any object, direct or indirect object, whether it be letter or her, they would be appearing on the other side. So that was what the last criteria is implying. So these are the different criteria. Based on that, we know that 2 and 4 would be correct. So correct as in, so those are the invalid options that are present. So as correctly explained by Archana, so here options 1 is correct. Option 3 is also correct. We just discussed. So remaining 2 and 4, they are incorrect. They're actually opposite of what are the valid criteria. So that makes them invalid. So 2 and 4 would be the false statements over here.
Ma'am, I have a doubt.
Yes.
And what's the difference between the fourth statement and fifth criteria? What is the difference? The H, based upon the head, is whether it is mandatory or optional, it is same. And in the fifth statement, also the form of D depends on the H. What is the difference between these two criteria?
Um, okay. So, for example, let's change the sentence a little bit. So, let's say that instead of he sent her a letter, or just a second. Okay, so let's take a different sentence. So, first to understand this one, to understand the fourth criteria. So let's take the sentence that she ate an apple. Okay, so here the word ate requires a subject and an object, a direct object. Okay, so we need to specify who is eating and what is the person eating. Whereas if we consider, so in this sentence, the example that I gave here, uh, 8 would be the head, and it is determining which are the dependents that are obligatory. The dependents that are obligatory in this case are the subject and the direct object. Whereas if we consider this sentence that is given in the slide, here the head is sent. So the verb sent requires three things. One is the subject, who is sending. Next is an indirect object, to whom is the person sending. Third is what is the person sending, and a direct object. So for this verb or this head in this case, so here send is a head, right? So here it is making obligatory that it should have a dependent which is a subject. So you should have three dependents, mandatory, obligatory dependents, which is subject, direct object, and indirect object. Whereas if this would have been 8, as I mentioned it, so only subject and direct object would have sufficed. So I think that answers the fourth point. Is it clear?
Yes.
And so the fifth option would be, say if you take the example of let me think for a second. So you can further read on this. This is a very interesting thing. So there's this notion of grammatical agreement where the subject and verb agreement takes place. So it can be either in the grammatical number or in the person or in the, so mostly in these things. So you'll see there's an agreement that is happening. For example, uh, okay, so for example, I have a book, okay, whereas if I, instead of I, so I is first person, if I change it to she's a third person, right? So it would be she has a book. So this is where, so in both the cases, I and she are the subject, and the verb is in one case have, and another case it's has. So this is subject verb agreement. This is one notion of agreement. Similarly, there's also the notion where number needs to be maintained. For example, they have books. So here, when I'm changing it to they. So they is third. So she was third person singular. They is third person plural, right? So here when I'm changing the number, again the verb is changing. So there are different grammatical agreements that needs to be satisfied, and these are necessary to make this sentence grammatical. Otherwise, the semantics, you'll be able to understand what is the meaning of the sentence, but it would not be a fluent English sentence. Okay, so that is what it means. Thank does anybody have any other doubt in this question? Okay, so let's try the next problem. So in this problem, we are given the sentence, Ramesh scored a brilliant century. We have to say that the relation century to brilliant, what type of a relation it is. Is it endocentric, exocentric, or both, or none? So please give the problem a try. And again, we'll try the problem we'll wait for 1 or 2 minutes. Meanwhile, you can post your answers in the chat and then we'll go ahead with the discussion. Okay, I think we can discuss the solution. Um, so first, let's discuss what are the concepts of exocentric and endocentric. So this is taken from the slides itself. So let's take the sentence: economic news suddenly affected financial markets. So here we have to identify what are the exocentric and endocentric constructions. So first, let's get started with endocentric construction. What does endocentric mean? Endocentric means one entity that is present can fulfill the grammatical function of the whole construction. Say we take this suddenly affected. Here, affected is the verb, where suddenly is the verb which is further specifying the verb. So it is a verb modifier. So this is an example of endocentric construction. Why? Because here the whole construction is suddenly affected. However, if I simply retain affected and omit the word suddenly, I still have a valid sentence. So if I omit suddenly, what would the sentence be? Economic news affected financial markets. Okay. So here I see that so here the whole construction can whole construction can be replaced by the word affected. Okay, so this is an example of endocentric. Let's take another one. So another example is financial markets. See here, here we have the word markets, which is being further specified by the noun modifier financial. So it's telling what is the type of markets that is under concern in this sentence. So economic news affected the financial markets. So here again, if we drop the word financial, we still have a valid sentence since markets is fulfilling the grammatical functionality of the whole construction. So these are examples of endocentric constructions. So over here, one thing that we need to identify is so given the construction, which are the head and which is the dependent. So head is the one which is the main part of the construction, which is conveying the grammatical functionality of the entire construction, which is affected in this case, markets in this case. And obviously the second one, which is certainly and financial, which we're further specifying or further giving additional information about the head, is the dependent. Now another type is exocentric. So exocentric constructions would be of the form verb subject, verb object, where all the entities that are present in the construction are mandatory. So for example, here news is my so affected is the verb and the subject to affected is news. So here I need to, so both news and affected are required to be present in the construction. I cannot drop either one of them and say, okay, I'm still having a valid sentence. That is not there. Both of them are necessarily to be present in the sentence. Similarly, if I take affected and the object of the sentence, which is markets, though that information also needs to be present. I cannot drop any of these words. So these are examples of exocentric constructions. And in such cases, the verb which is affected would be the head, and so the subject, which is news, and the object, which is markets, those would be the dependent. So here the word is here the construction that we are concerned with is century to brilliant. So this one. So here we observe that century is the noun and it is being further specified, further modified by the word brilliant. So that tells us that what kind of relation it is. It is an endocentric relation. So even if I drop the word brilliant, so Ramesh scored a century. Still valid enough, still gives a, still I'm still able to capture the semantics or the meaning of the sentence, right? Brilliant is simply an adjective which is further specifying like um, further providing additional information about how the century was. So, so we come to the answer, which is option one, which is androcentric. Is this clear? Does anybody have any doubt? Okay, I hope it's clear for everyone. We'll go on to the next question. We can come back later if anybody has any doubt. So this question is about data-driven deterministic parsing. Here we have to mention among the four options that are given, which of them are false. So again, this is a direct question taken from the slides. So I expect everyone to just give it a try once and please post your answers as well in the chat. We'll wait for 1 minute and then we'll go ahead and discuss. Okay, so two of you have answered. We'll discuss. So meanwhile, Ashutosh is asking which number. So we are discussing practice problems actually. We are not discussing any specific assignment problems. These are just practice problems from week 6 content. And so we're currently solving the fourth one. So Archana and Shubha have answered. So let's hear from Shubha this time. Shubha, would you like to say why you think option 4 is correct? You have mentioned though that you think the other three are true. Just to maybe some further clarification, if you would like. Okay. Uh, okay, no problem. Um, so Archana has also said that it's option 4. Archana, would you like to say?
Yeah.
Okay, okay. So that was correct. So would anybody like to also add in? Anyone? So today we have 18 participants. Would anybody else also like to say, comment anything else? All right then. So I think we can just discuss the official solution once. So for data-driven deterministic parsing, we have the following things. So there are three things that are there. So deterministic parsing. So in the lectures, two types of deterministic parsing were discussed. So in each of the algorithms, we saw that deterministic parsing requires an oracle, and then an oracle can be approximated by a classifier where from the training data we were learning, right? Sometimes we're learning the weights, sometimes we're learning what are the possible arcs, all these things we're learning, right? Those are there, and a classifier can be trained using tree bank data. So these are the three characteristics that are inherent to data driven deterministic parsing. And so these are the three options. These are exactly the three options that are there. So all three of them are correct. That leaves us with option 4. It is none of this uh, to be the correct solution for this question. Does anybody have any doubt?
Ma'am, would you repeat once again the solution?
Yes, sure. So we were talking about data-driven deterministic parsing. So in data-driven deterministic parsing, there are in the lecture videos, there are two things discussed. So one was the transition-based dependency parsing that was discussed, and other is the MST-based deterministic parsing. Both are data-driven deterministic parsing. So we observe that in data-driven deterministic parsing, what happens is we require an oracle. So the oracle is required so that it can be approximated by a classifier. So classifier is required because at each step we need to take decisions from multiple options. So that is why we need a classifier. And how and where does machine learning come into this context? Machine learning comes because we are given data, we are given training data, and we are training the classifier using the training data. So that would be specifically tree bank data. So that is giving us, like, say in when we are doing transition based parsing, so at any given configuration, which transition should we take? So there are four. Should I shift? Should I reduce? Should I do a left arc transition, right arc transition? All these things. Or so there are other examples also in the lectures if you just go through that once. So all these things will be determined based on what are the statistical evidences that are present in my training data. So based on these, so these are the options. The first one is deterministic parsing requires an oracle. So so the first one is correct. Second one is an oracle can be approximated by a classifier. That is also correct. Third is a classifier can be trained using tree bank data. So the first three options are correct. However, the question asks what which of the options are false. So none of the options are false. That is why I have option 4, none of the above, to be the correct answer in this case. So all these are, like, as I mentioned, these are specific characteristics for data-driven deterministic parsing specifically. So is it okay now? Okay. Let's discuss the fifth question. Okay. So in the fifth question, what is mentioned is, so we are given the sentence, I prefer ChatGPT posts. So we have to do the transition-based parsing. So using the transition-based parsing, I have to say that how many times I have taken a right arc transition, left arc transition, reduce and shift. So this is what I need to say. So these are the numbers corresponding to each of the transitions. Also, it is one thing that you need to note over here is that we have to assume that the sentence is there in my training data. So you are already aware what is the gold standard uh, solution for this. So you know what is the dependency pass should be for this sentence. Based on that, you have to do the transition based dependency passing and find out what are the transitions that you need to do at each step. Please try this problem once. This is a very short sentence, an easy problem. Just try this once. And once you're done with the solution, post your solution in the chat and we'll take it up in a couple of minutes. So I think none of you have yet posted the solution. Um, I think maybe we can directly jump over and discuss how to solve this problem. So this problem and the next problem are actually related. So here we have been asked to find the number of the number, whereas in the next one we'll see, this is the sixth question, we have to specify what was the sequence. That was what is the sequence of transitions that were taken. So we'll discuss both of them together itself. So let's see how to go about this. So first we need to know what is the gold standard dependency pass for this sentence. So here the sentence was, I prefer ChatGPT course. So prefer, which is the verb, that is the root, or that is the head. The corresponding dependency is, so there's a subject dependency to I. So I is the subject. So this is one of the dependencies. Another one, so I have a direct object in this case, which is course. And ChatGPT specifying what kind of course is it that I prefer. So it is further specifying the noun over here. It's a noun modifier. So this is what is given to us. Now, based on this, I need to do the transition based dependency parsing. How should I do this?
And this won't be given in the question.
It is mentioned that it was a gold standard pass. So it was in your training data. So you have to construct this on your own. Yeah. So now let's see how to go about it. So, so in dependency paths, we have three things. We have a stack, we have a buffer, and we have an arc. Okay. So initially when I start, so what are the initial conditions? My stack would be empty. What is stack? Stack is the partially processed words. So initially when I start, so none of the things have been processed. So the stack would be empty. The buffer would contain all the words, which is I prefer ChatGPT and course in this case. And arcs is also empty. So there's nothing right now. So in this case, we know there are four possible transitions that I can take. It could be shift, it could be reduce, it could be a left arc, it could be a right arc. So in this situation, what should I take? What transition should I choose? Let's just think over each of the transitions once. Can I take a left arc over here? So if I want to take a left arc, it would mean that the left arc would be from the top of the buffer, which is I in this case, to a word in the stack. But however, the stack is empty, so that won't be possible. So left arc is not a valid choice. Next is right arc. So if I had to have a right arc, the right arc would be from a word which is in the top of the stack to the buffer. So again, the stack is empty, so right arc is again not a valid option. So left arc and right arc are eliminated. Okay, so those are not possible. Next is, can I do a reduce operation over here? So in order to do a reduce operation, there should be something present in the stack. Again, the stack is empty, reduce cannot be done. So that leaves us with the shift operation. So in shift operation, what I do, I take the word that is in the top of the stack and push it to the top of the, okay, take the word which is in the top of the buffer and I push it to the top of the stack. So that is what I'm doing. So first I'm doing a shift transition. So after this, the next intermediate configuration that I have is, so now I have I in the stack and prefer ChatGPT and course, these three words in the buffer. So now again I'm left with the same choice, that among these four possible transitions, which one should I take? So what I need to do is, here in order to understand, in order to find out what is the transition that I must take at this point, and to look at the dependency graph that I have, or the dependency graph that I want to obtain. So which is this one. Okay, so here I see, so here again let's look at the words. So I is here in the stack and prefer is here in the buffer. So these are the words that are there in the top of the stack and top of the buffer respectively. So if I look at the dependency graph, so am I able to establish a relation between the top of the stack and the top of the buffer in this case? So yes, indeed, I can. So here I see, so this word was in the top of the buffer and this was in the top of the stack. There is a relation. There's a subject relation. So what can I do in this case is, I take a left arc from prefer to I, okay, and I do a left arc transition. As a result, I would be removed from the stack. Buffer remains as it is, and this is the arc that I've added, okay, prefer to I, okay. So this is what I have right now. This is my current intermediate transition. Next, what should I do? Next again, so since the stack is empty, following the discussion that we had in the first step, when the stack is empty, I cannot take a left arc, right arc, or reduce. None of them are feasible. I can only do a shift transition. So in shift, I take the word that is in the top of the buffer and place it in the top of the stack. So here prefer has gone to the stack, and what remains in buffer is ChatGPT and posts. Okay. Now at this point again, I need.
Sorry.
Yeah, yeah.
Order of the buffer is a shuffle and view. We just can we use other variables to start?
Could you please repeat your question once more?
I mean, here the buffer is in the same subject or object fashion. So order it keep shifting, we get the preferred sentence out of it.
Hmm.
If
So,
it is preferred, suppose we assume in this case prefer post chat GPT and then I word is like the buffer.
okay.
And do we have to arrange the buffer first in the required sentence form?
So the words in the buffer would be as per the words that are there in the sentence. So this is exactly how the words were ordered in the sentence, and they need to be placed in the same order.
If at all there is a shuffle, is there any mechanism to arrange the buffer? Do we have to consider any transition?
If the words in the buffer are shuffled, so uh, I mean, shuffling would actually, if you shuffle the words, then I don't think the algorithm would hold. It's a necessary condition that words should be placed, and so we handle the words in the order they come in the sentence. So the word order is necessary.
So if they are not given, if they just give a sentence, we have this basic in the buffer.
Correct. Correct.
Because this stack and buffer words are we put multiples into the stack and buffer and buffer is for multiple times transition. What I assume.
Okay. Okay. Yeah, so you need to maintain that. I mean, I understand. So you're maintaining multiple lists at the same time, so it can be a cause of doubt. But the word order is very important. If you change it, you'll get some abrupt answer which makes no sense. So Vandana has raised her hand. Yes, Vandana.
Ma'am, here shift operation, shift transition means to shift the word in the stack.
Shift transition means you take the word which is there in the top of the buffer, and you move it to the top of the stack. So here, for example, prefer was there, right, at the top of the buffer. So I now place it at the top of the stack.
So where did I
There is I. So I was removed over here. Whenever we do a left arc transition, so we had the left arc from prefer to I, right? So I is dropped, and so the word that was there on the top of the stack, that is dropped whenever there's a left arc transition. Um, just a second. Maybe if I open the slides. Um, hmm. So I'm sharing the slides right now. Hope it's visible. Yeah, so here you see whenever we do a left arc, right? So the thing that is there on the top, that is the configuration that we start with, and the thing that is there in the bottom is the configuration that we end up with after we have performed the left arc transition. So here we see that after we perform the left arc transition, the word that was there on the top of the stack, which is WI, that is dropped. Okay, here you see the WI is no longer here at the bottom. Whereas the buffer remains as it is. We simply to the A is the list of arcs that we are maintaining. So we simply add uh, the left arc that we just now found. So that would be the configuration that I get after left arc transition. Is it clear, Vandana?
So, ma'am, reduce means also to remove the word from the.
Reduce also means to remove the word from the stack. However, there's a criteria. So here what you see here, head WI. So you can only remove the word WI from the stack only if the word has a head. Okay, if the criteria is satisfied, you can remove it from the stack. Here, for example,
It's confusing for me.
uh,
Art means is what?
arc means here, for example, go over to the slides again. Arc is this. Prefer to I. You see a arc over here. There's an arc from course to chat GPT. All these are arcs. So similarly, so this is a left arc, right? From prefer to I, this is a left arc. Whereas from prefer to course, this is a right arc. Hmm. So that is what we are doing over here. So here, from prefer to I am drawing a left arc. And whenever there's a left arc, I drop the word that is there in the top of the stack, which was the dependent in this left arc transition. The dependent was I, right? If you look at this left arc, prefer is the head, I is the dependent, right? So we drop it because there's no further relation that could be established with the rest of the sentence. So no further processing needs to be done for this particular dependent. So we drop it from the stack. So its processing is complete. It's no longer partially processed, it's completely processed. So you drop it.
So means here had means from which the art is initiated.
Pardon?
Here is had means that means that prefer is had and I is had on the prefer.
Mm-hmm.
So how we decided this is had? Had means from where art is
Correct,
initiated.
correct, correct, correct. Also, we saw in a couple of slides back to determine which is the head, which is the dependent. Here we see that it was a verb-subject relation, right? In the example that we are currently doing. So there, prefer is the verb, I is the subject. It's the exocentric construction. So here the verb would be the head. So prefer would be head, and I, which is the subject, it would be the dependent. Is it okay?
Okay.
Okay. I think we have a couple of more steps left. I think by the end, I hope you'll be able to understand. Otherwise, you can again like ask doubt. So let's go on to the fourth step. So we were here, right? So here again, so here my current configuration is I have prefer in the stack and I have ChatGPT course in the buffer. So now again, what should I do? Here I have some words in the stack. I have some words in the buffer. Can I add any arc? Can I do any can I establish any relation between the words here? So the thing that we need to check over here is first let's take the words that are there in the top of the stack and top of the buffer. So that is prefer and chat GPT. So so if I look over here. So prefer and ChatGPT, do they have any arc, any right arc, any left arc? Nothing. So here, left arc and right arc are not valid transitions, so they're eliminated. What are the remaining options? I have reduce and shift. So between reduce and shift, what should I do? So here in the slide, in the lectures, a thumb rule was mentioned. So thumb rule is if the word that is there in the stack, whether it's be top of the stack or before the stack, in this case here is only one word, but there could be other sentences that when you're running transition based dependency passing on, there could be multiple words in the stack. So for words that are there in the stack, you see that are they connected to any word that is there in the top of the buffer? So it's no. So there it is not the case. If it was the case, then you do a reduce operation. Since it is not the case, here we do again a shift operation. And so we shift chat GPT to the stack now. And so this is my current configuration. Now again I check what are there in the top of my stack and top of my buffer. Chat GPT and course. Was there a relation between chat GPT and course? Yes, there is a relation, noun modifier relation. So ChatGPT is further specifying or giving additional information about what type of course it is. So here we can do a left arc again, right? So I have a left arc. Left arc is from the top of the buffer to the top of the stack. So I add the left arc and I do the left arc transition. Okay, so this is done. So when I do a left arc transition again, so the word that was there in the top of the stack that is dropped. So ChatGPT is dropped. So what remains is prefer uh, is the word that remains in the stack, and course is the word that remains in buffer. Now between these two words, I again need to check is there any relation in my gold standard data. Prefer and course. Yeah, so course is the direct object. So there's this relation. What is this? This is a right arc. So here we do a right arc. Right arc is from the top of the stack to the top of the buffer. So whenever we do a right arc transition, what happens is the word that was there in the buffer that is shifted to the stack. Nothing is dropped, just the word is added. So currently, this is my final configuration. Prefer and course are there in the stack. Buffer is empty. As soon as I see if the buffer is empty, it means I've reached my termination condition. And so these are the sequence of transitions that I took. These are the arcs that I obtained by referring to the core standard dependency paths that I had. Okay. Um, so yeah, so this solves both the fifth and the sixth problems. So here let's count what are the different operations that I took. So here there are 3 shift operations, 2 left arcs and 1 right arc. So that was asked in this question. What are the number of shift operations? 3. What are the number of reduce operations? It's 0. Left arc is 2 and right arc is 1. So here option 3, which is 1, 2, 0 and 3, this is the correct answer for question 5. And if I look at question 6, here it was asked what is the sequence that I took. So what was the sequence? First period a shift, then left arc, then again 2 shifts, then finally a left arc and right arc. So that would be the first option. So this is how we solve questions 5 and 6. Any doubt in these questions?
Ma'am, in this, please go to the table. Yeah. In this, the stack four, where four after four shift, you have not removed the prefer because there is no relation. I mean, there were no arc and relation between the prefer and chat.
I did not remove prefer. So remove, we cannot just abruptly remove a word from the stack. So we can only remove in certain cases. So let's see. So I'm again sharing the slides. So see in what cases can you remove a word from the stack. I'm moving my cursor over those. So when I do a left arc operation, you see just focus on this part, okay? You see, wi was dropped, okay? Here when I'm doing a right arc, you see wi is retained, so no word is dropped, only wi was there in the buffer. I move it from the buffer to the stack when there's a right arc operation. When there's a reduce operation, again the word wi, it is dropped, okay? And in shift again, so I'm taking a word from the buffer and adding it to the stack. So only in these cases, left arc and reduce, I can drop the word that is there in the top of the stack, not the words that are previous to it. Okay, so if I go on to the slides again, so here you're asking about prefer, right? Prefer could not be dropped in this situation. Chat GPT could, however, be dropped because it is there in the top of the stack. But for Chat GPT to be dropped, either two things should have been there. The transition that I take at this step should be either a left arc or a reduce. So here I've taken left arc transition, so I was able to drop ChatGPT in the next step, or in the current step itself. So did that make sense? So there are sequential steps, I mean, that you need to take. Um, uh, was it clear?
Ma'am, we can't reduce the pressure. I mean, my question is that we have not moved from the that pressure because there is no art is matching here the pressure to the chat.
No, no, that is not the reason. I mean, so you cannot remove prefer over here. Prefer can only be, so a word in the stack can be removed only if it appears in the top of the stack. Also for prefer, all the arcs or all the transitions that are there, those have not been handled. This still partially processed. If that is what you're trying to say, this still partially processed. Further processing is required. Only once a word is completely processed, you can remove it from the stack. Vandana, is it okay?
Actually, I'm taking it just like there are art is related to the iron first, so we have the shift and there is art between the chat GPT and pose, so we have some again lab art and there is also art between the picture and pose, so we have also done art but not understand. So I am relating it just like the picture has no direct relation to the chat GPT. That's why we have keep it in that chat.
Um, so So we actually need to approach the problem in a different way. I think you're thinking from a more intuitive point of view. You're relating different words and their dependencies. So that is good for like a high level intuitive understanding. But if you're trying to do transition based dependency parsing, in that case you have to be very systematic about which transition you're taking, because each transition has certain criteria that are governing each of the situations. Maybe if I discuss that once, maybe that would be make it clear. So let's discuss this once. So I'm sharing the slides. So here you see that whenever we take a left arc, right? So initially we start with this configuration. After we take a left arc, the word that is there in the top of the stack, that would be removed, and the rest of the things. So the buffer remains as it is, and we add the dependency that we just found, the left arc, uh, in the list of arcs. So what is the left arc? Left arc happens from the top of the buffer to the top of the stack. So from wj to wi. Okay. So this is the scenario. Similarly, if I go for right arc happens from the top of the stack to the top of the buffer. Okay, so from Wi to Wj, that is how it would happen. So note the direction, note how we are operating. So we are always operating uh, on words that are there on the top of the stack and on the top of the buffer. We are not taking intermediate words or words that are there before Wi in the stack, that are placed before Wi, or the words that are placed after Wj. We're only handling words that are there on the top. Either we do a left arc, either we do a right arc, either we drop the word or we add the word. Either we drop the word from the stack and reduce, or we add a word uh, in the stack from the buffer and shift. So that is how we go. So we have to be these are very systematic steps you need to do. Otherwise, if you misplace any word during the transitions, your overall calculation would it would go wrong. So I think if you go through the lecture once, so Sir has explained this with examples as well. So there was an example similar to what we did just now in the slides. So I think if you go through the lecture once more, a couple of more times, it would be clearer.
Okay.
Okay.
And this, when we are saying it is left out, right out, we can
Yes.
see the reference from top of the buffer out to the top of that, right?
Yes.
So when we said this is a left out from the row 1 to 5th row, we said it goes to ChatGPT as a left out.
Hmm.
And we say right out, both is in the buffer and the prefer is in the top of.
Yes.
And this time right is in the stack buffer.
Yes. Correct.
So the reference changes, right? It is right and left.
Yes. So the words that you consider for the dependency would be the words that are on the top. So for a left arc, the head would be the word that is at the top of the buffer. From there, you're starting the arc, and it is going to the top of the stack. So here, the word that is at the top of the stack would be the dependency in the left arc situation. Whereas in the right arc situation, the top of the word that is in the top of the stack, that is the head. You start from there and you end your dependency in the top of the buffer. So top of the buffer, that is course over here, would be the dependent word in this case. The direction changes. Left arc is from buffer to stack, right arc is from stack to buffer.
But the origin is not always consistent.
No. It's from buffer to stack is for left arc only. Always for left arc, it starts at buffer. Always for right arc, it starts at stack. Okay. And whenever the stack is empty, you just do the shift transition. Yes. Okay, let's discuss the next problem then. So here in this problem, we are doing the MST based parsing. So we are given the sentence, I like online exam. Here the few tags are given. So I is pronoun, like is verb, online is proper noun, and exam is noun. Also, for simplicity, we are assuming there is only one dependency relation, which is REL. Now, these are the features that are given. Based on these features, and also the feature weights that are given at the start of the iteration, that are these. Now, using the algorithm, we have to find out what would be the weights after this iteration. So these are the options. So please try this problem once. So Arjuna is saying, can we discuss a problem related to reduce? We'll take it up. We'll just maybe a few two, three more problems are left for the practice session. We'll just complete them quickly, and I'll take up a example related to reduce as well. Okay, let's discuss. I think there's been... Okay, nobody has posted the answer. Let's discuss then. Let's discuss how to go about solving this problem. So, first, what we need to do is here one thing that is given to us is so after applying the algorithm, the path that we obtain that is given to us. So there would be an arc from root to like to I to online, and online to exam. Okay, so uh, that is what are the arcs that I have drawn over here. You also see the pure tags corresponding to each of the words. Okay, so now what we need to find out is what is the, so we know we need to find out what are the features corresponding to each of the arcs. So how do we find out the features? So these are the features that were given to us. Okay, these are the four features. These are all binary features that would take a value of 0 or 1. 0 if it's not satisfied, 1 if it's satisfied. The first feature is pure tag of wi is verb and pure tag of wj is noun or pronoun. Let's see. So let's take this arc. So this is wi and this is wj. So the start of the arc is wi, where it ends is wj. So is this verb? Yes. Is this a noun or a pronoun? Yes. So it has a value of 1. Let's take another one. Let's take this online exam. So here is this a verb? Is wi a verb? No. So it is 0. What about this one? Again, no, wi is a pronoun and not a verb. So this would be 0. Similarly for the other cases. Let's take another one. Mm, let's take F4. F4 is WJ occurs before WI in the sentence. Okay. So again, uh, let's take this one. Again, this is WI and this is WJ. Does WJ occur before WI in the sentence? Yes, I occurs before like in the sentence. So this is true. So this is one. How about this one? Let's take this arc. Here this is I is WI, this is WJ. Does WJ occur before WI in the sentence? Does online occur before I? No, online occurs after I. So it is false. So here the value is 0. Similarly, you need to find out for each of the features, for each of the arcs, what are the feature values, and this is what you will obtain. Okay. Once that is done, this is G dash um, or the value that you get after the iteration. Okay. Uh, next is so here what I have is just a second. So here what I have is here if you see, so this is GT. GT is the goal level. Goal level. What is the actual dependency pass? So here I see from like to I, there would be an arc. From like to exam and online. So an exam to online again. So this is the actual goal standard data. So here again we need to find out what are the values for each of the features. Let's again try for one more. This time let's take a different one. Let's take F3. F3 is WI is root and Pierce tag of WJ is verb. Let's see. Um, let's take this one or let's take this one. So here WI is root, Pierce tag of WJ is verb, correct. So that is why F3, which is this one, the third one, that is 1. Here, let's see, here is WI root, no, so it's 0. Let's see here, WI is again not root, so it's 0, and here also it would be 0. Okay, that is how you similarly, like we discussed in the previous slides, similarly here also you need to find out the values of each of the features. Okay, because what we have been asked is W new, what is the weights after this iteration, and for us to do that, we need to find out the values of f of gt and f of g dash. So what is f of gt? F of gt would be summation of all these features. Okay, all these feature vectors. If you sum those up, you will see you will get this. F of g dash will be similarly, you have to sum up all the vectors, but now this time for the graph g dash. So if you sum up all these things, you'll get this. Okay, and W old was given to us. It's 5, 20, 15, 12. It was given in the problem. Now we simply plug in the values in the formula. So this one plus you take a difference of these two. Okay, how is the feature different? So how is G dash, how much does it differ from the gold standard? Okay, so you simply take a difference and you find the new updated weight. So it would be 6, 19, 15 and 13, which is this one, option 2.
Ma'am,
Hmm.
how how we will get the app details? Means FGT is okay, we have summation or feature values
So,
or weight.
so here also you have to add. So if G dash would be, you sum these. This one plus this one plus this one plus this one.
So
So
the addition of these all will be FGT.
FGT would be this one. The GT and G are different. The graphs are different. So this is GT. GT is the gold standard one. G dash is the one that is under the current iteration, the graph that you obtain after the algorithm in the current iteration. That is G dash. FGT is just summation of the feature vectors for each graph. Is it clear?
That was GT or G dash, where we have multiplied, where we have taken the future value to put on here.
So in each GT and G dash in both you have to compute the features corresponding to each of the transitions. The feature vectors are given, not feature vectors. The features are given. These are the 4 features, right? Now wherever there's a transition in any graph, you have to compute what is the value for each of the features. So I think in the lecture also sir has gone through a similar problem. So there also I think sir has discussed the same thing. So this is like a simpler and smaller version of that. I think if you go through that once, I think it would be clearer. Otherwise, we can take this up again. I mean, I think we have a similar, yeah. So this is the this one you're saying, right? This is the gold standard. Gold standard is this is the correct one. So you have to find this out yourself. So this is not given in the question, but it is mentioned that it occurs in the training set. When it is mentioned that something occurs in the training set, it means it has a gold standard available with it. Gold standard is the correct dependency pass. So for the sentence I like online exam, this would be the correct dependency pass if you do it. So always when you're doing the correct dependency pass, the root would be directed towards the verb and everything else starts from the verb. Verb to subject, there would be a relation, that is verb that is like to I. Verb to object, there would be another arc, and again then see what other things remain. Here you'll see that online would remain, and online is modifying exam, so there would be an arc from exam to online. So verb to object, object is exam in this case. So yes, from the question you found the values. So in the question, these 4 features were given, F1, F2, F3, and F4. So you computed that for each, for this arc, and that gave you 1100. Is that okay? Uh, okay. So, okay, so let's take this one. Like an exam. Let's take this arc. Let's take one of the features. Let's take F1. F1 is POS of WI is verb and POS of WJ is noun or pronoun. Okay. So here this is WI. Like is WI. Exam is WJ. So is POS tag of WI verb? Yes, it is. And is POS tag of the WJ is noun or pronoun? Yes. So I get 1. Similarly, for each of the other features, there were 3 more features you need to compute. And that would give you a binary value, 1 for true and 0 for false. Yeah.
Ma'am,
Yes.
ma'am, GT and G dash, the graph or the transition graph that you have drawn are different.
Yes.
In the question, like directly go to the exam, but in the G dash, I go to the
Yeah.
how it how it
So G dash is given in the problem. You see, it's given that after applying the algorithm, you get these arcs: root to like to I to online, online to exam. following these arcs, you have drawn G dash. Okay.
Yeah.
Now, whereas GT, this you need to figure it out yourself. This is the gold standard data. And how do you get GT? Again, in the question it needs to mention that the sentence, I like online exam, it occurs in the training set. When it occurs in the training set, corresponding to the sentence, the original gold standard dependency part should also be available. So, and this would be the gold standard dependency pass. Gold standard means correct dependency pass for this sentence.
So, ma'am, how
How to draw the correct dependency pass in this case?
there were I like online exam.
Hmm.
So these transitions,
So
how we do.
So this, I mean, I can give you an example over here, but this more you practice, you'll uh, be able to do it. So here, wherever you're doing dependency passing, you have to remember the root is should always be pointing to the verb. So what is the verb in this case? Like. Okay, so this would be there. Okay, this you can most of the time you'll have this one. So root would be pointing to the verb. Now from the verb, you need to figure out what are the subject and the object that are present in the sentence. So starting from the verb, there would be an arc to the subject of the sentence, which is I, which gives you this arc. Okay. So you have right now this one, this one. Now again from the verb, there would be one more arc to the object. So here the object is exam, so that gives you this arc. Okay. So these three are now done. Now you see the word online is isolated. You haven't find out anything. You still need to understand what is online. So remember the endocentric and exocentric relation. Think about that over here. So your online exam is it is a endocentric construction because online is further specifying or giving additional information about the word exam. Okay, so it is a modifier. So here in this case, online would be the dependent, exam would be the head. So this is how you draw the arc.
So, ma'am, if we are taking here life as a verb and other to the fact, this is related to I, subject and object. So here is and exocentric
Exocentric. Yeah,
and online and exam. Okay, okay.
correct, correct, correct.
It's not like one can do this root you need to consider to the word directly, but feature values onto the root.
It is for this arc. I've written it there. It is for this arc.
Yeah, we consider with reference to life and root.
Yes, where
Root is
wi would be root. Pa-
um,
Pardon?
what is the price of the root?
PS of the root is nothing. So whenever that would come, it would be automatically zero. Whenever it's given, right? PS of wi is verb, PS of root is nothing. So automatically the feature for that arc would be zero that you can observe over here. Okay. Any other doubt?
Yeah.
Okay. Let's discuss the next problem. So it is which of the following is true about the formal conditions in a dependency graph? So this is also a very direct question. Just try it and we'll wait for 1 minute and then we'll jump on to the solution. Okay, so some of you have answered the question in the chat, and so most of you agree that option 4, that is both 1 and 3, are correct. Let's quickly hear from one of you. So, Lokesh, Archana, Vandana, 3 of you have answered. Let's hear from Lokesh maybe.
Yeah. The gram G is connected and projected. There is no isolated vertex visible in this. It is left over
Hmm.
and
Yes.
which an navigation from where the one and so it is projected. And cyclically, there is no cyclical self edges. A to B and B to A is not possible.
Okay.
So the third one is cyclic and always a single head transfer. It will be always having the outgoing
Okay.
button.
Okay. Um, okay. That was, yeah, correct. How about others? Would anybody like to add on to what Lokesh has said? If not, then we'll discuss. So the answer is 4. It's correct. Let's just quickly discuss uh, what are the different characteristics. So G should be connected. The graph should be connected. So if there's a node I, so for every node I, there's a node J such that there is an arc from I to J or J to I. Okay, either one would be there. Okay, next is the graph is acyclic. So if there is a arc from I to J, there cannot be a path from J tracing back to I. Okay, that is not possible. G obeys the single head constraint. So if there's an arc from I to J, so I is the head for J in this case, then K to J, where K is again a head for J, that is not possible if K and I are different. And G has to be projective. So if there's an arc from I to J and J to so there's an arc from I to J and there's a path from J to K. If that is the case, then J and K should lie on the same side of I. So these were explained in details in the slides. So I just quickly just discuss them once, just for everyone to just for a brief recap. We can, I think, if does anybody have any doubt in this question? Okay, let's go on to the next problem. So in this one, we are given this graph. Now the question is, which pair of the nodes will be contracted to form a single vertex during the algorithm in the first iteration? So this is based on the algorithm, Chulio-Edmonds algorithm. We discussed 2 problems, I think, today on this algorithm. So just try this for a minute and then we'll discuss. let's proceed with the solution. So in this case, again, we need to, so so what we need to do is in the first step, for each vertex in the graph, we select the incoming edge with the highest weight. Okay, so let's do that. So for V1, we look at the incoming edges. What are the incoming edges? One is this one with a weight of 5, this one with a weight of 10, and this one with a weight of 9. So which one is retained? This one, G10. Okay, so this one, correct? Next, if I look at V2, what are the incoming edges? One is this one, which is which is the edge B with a weight of 1. Next is D with a weight of 11, and we have this I with a weight of 8. So which is the maximum one? This one, D11. So this one. Next is for V3. We have this one with a weight of 1, this with a weight of 5, and this with a weight of this one, E with a weight of 4. So here F, the edge F which has a weight of 5, that is the incoming edge which has the maximum weight. So here we retain this one, F5. Okay. So according to Chu-Liu-Edmonds algorithm, whenever we have a cycle, we identify the cycle and we contract it into a single vertex. So here cycle has been formed between the vertices V1 and V2. So they need to be contracted into a single vertex. So that has been asked in the algorithm, that which pairs of nodes have to be contracted to form a single vertex, which is V1 and V2. So that gives us the answer. That is answer is 4. Does anybody has any doubt in this problem?
Based on the highest weightage.
Yeah. We take the incoming edge with the highest weight.
Yeah, first we before that, but there is V2 to V3 also there is cycle.
V2 to V3. No, there's not a cycle though, right? The cycle is here.
Oh, only with the highest edges we see where it is.
Yes, yes. In this graph that you obtained.
Ma'am, will you go to the tree? Yeah. As per the rule, you have to take the highest weightage according to ED manner. So why we have not taken the A5 that have the weight highest?
A5, this one. So A5 is the incoming edge to V1, right? So let's look at all the incoming edges to V1. A5 is there, and G10, that is also an incoming edge to V1, correct? Right? And A,
So ma'am, in this we have to look incoming edge on a particular vertex.
for each vertex. So for each vertex in the graph. So here the vertices are V1, V2, V3, which has incoming edges. Root only has outgoing edges, right? There are no incoming edges. Forget about root right now. So we have V1, V2, V3. For each, we have to take V1, see what are the incoming edges. These three. Which is the maximum? This one. Take V2, what are the incoming edges? Like that you have to go.
Yeah. And the weight 2, 5, 1, 4. So 5. Okay.
Yeah. So is it clear?
Yes.
Okay. So this was the last problem for today. Um, So one of you asked me to explain reduce. I'll just quickly explain that. Huh. So let's see here. So I'm sharing the slides now. Yeah. So this is the one of the current configurations, the intermediate configuration. So now we have this sentence, he sent her a letter. So this is again a sentence that was there in the training data. So it has a gold standard uh, dependency parse tree available, which is this one. Okay, and we were processing the sentence using the transition based dependency parsing, and after a few steps, after 3 steps, we are here. So here now we need to see. Uh, so here I have the word sent in stack, and the words are her, a letter, and the punctuation mark full stop in the buffer. So first I need to see, so I have 4 options, left arc, right arc, shift and reduce. So for left arc and right arc, I need to see is there a relation between sent and her. So sent and her, there is a relation. So I'll take a right arc over here. Okay, so I take a right arc. That is what we do over here. So her is moved to the stack. Okay. Next, what we need to do now, here I have 2 words in the stack, sent and her, and in the buffer I have a letter. So now we need to decide, what do I need to do? Is there a relation between, so again I check the top of the stack and top of the buffer. Her and A is there. However, her and A, there is no arc between her and A. So I cannot do a left arc transition. I cannot do a right arc transition. The only possibilities are that remains are reduce and shift. So what do I do? Here I take the rule of thumb. Okay, what does the rule of thumb say? The rule of thumb say that I need to check that the words that are there in the stack, it may be, so it can be the word that is there before the top of the stack. So for example, say sent over here, sent is there, right? So we need to see, is that word connected to any other word that is there in the buffer. Okay, so we see, is that the case? We see that is sent connected to A. No, sent is not connected to A. Sent is connected to letter, however. So what we do, I think we'll do a shift over here, right? So we do a shift and we again move A over here. Now we again see that a and letter, they are connected. So how is the connection? The connection is a left arc. So I do a left arc over here. Finally, now I see that now we see that here sent and sent, so sent is not the top of the stack. However, it is connected to the top of the, so there is a connection between sent and letter. So letter is there on the top of the stack. So in this situation, what we do is we do a reduce operation. And we reduce operation, we reduce her over here. So if we reduce her, we need to check that her has a head. So we have added this connection sent to her. So there so the head of her is sent. So that criteria is satisfied. So I can remove her. I I do the reduce operation next. See, and I removed her, and now this is what I have. Now I can simply take a right arc between sent and letter, because we see over here that that is the connection. Okay, and then we finally obtain this situation where there's a punctuation mark. Again, for punctuation mark, I again need to do a right arc. Okay, no, sorry, we have to do a reduce again over here, because uh, sent and punctuation mark are connected, not letter and punctuation mark. So reduce, I remove letter. So now this is what remains.
Punctuation, right?
Pardon?
Letter and punctuation.
No, sent and punctuation. You see, I'm hovering over the arc over here. So now I finally make the connection. So this is again a right arc. So in right arc, what happens? The word that was there in the top of the buffer, that is pushed to the stack. So this is the next step. Now we finally come to the terminal condition where the buffer is empty and we have got all the arcs, and this is where we conclude the algorithm.
When you get away with the top of stack and keep it tight, reversal is not
And if we, so you asked if I remove a word that you say from the,
yeah.
if,
Reduce iteration, reversal is not
no. If you remove it, it means that it has been completely processed, and only then you remove it.
based on lectures they remove.
Yes. Any doubt, anyone?
Yes, any simple way to remember the sequence and types for all this and computer and the concepts.
For specific to dependency passing, this one you're asking, is it?
Yeah, passing, dependency passing, multiple types.
Uh, so I would say that transition-based dependency passing is it's more prevalent. If you understand transition-based dependency passing, others are simpler. So transition-based dependency passing, however, it is a bit difficult initially, but it is intuitive. So when you're trying, forget about the rules. Try solving based on your intuition. So try solving based on your grammatical understanding. Forget about left arc and right arc. Just think on what is the verb, what is the subject, what is the object. Is a word is so for example when we are talking about a letter here, remember what is the main word, what is a word modifying another word. Think on those terms, think intuitively, it would be very much easier. I think so.
Yeah, simple sentences somehow we can practice on the pragmatic sentences where we can define the previous question.
Okay. I think uh, in that case also try identify the main. Start with the exocentric relations, and then once you have those identified, you can find which are the modifiers. So modifiers you see are the ones that would be left behind after you process the main things, subject, object, verb. That any sentence is given, you can find out which is the main verb, which is the subject and object. That can be easily find out, right? So once that is done, then go step by step. First do that and then see what are the other words that you need to handle. And also check what are the phrases. So before this last week we spoke about constituency passing, right? There we are forming phrases. So here that concept also comes into play. So when you think about a letter, that is a noun phrase in itself, right? Think also in terms of that. So inside an
There at least there is a piece now, the grammar is there or we can see enough first.
how that is, yeah, that is true. I think if you just try practicing a few more, it would be like comparatively easier, I think.
Thank you very much.
Okay, thank you.
Ma'am,
Yes.
I have a query about the previous mechanism
Okay.
that we have listed on the bottom of the slide, where we have two parts, we have generally two parts to follow the
Hmm.
and there were two probability we find for both parts. And the question was asked in the assignment, at least one of the probability, find the probability for the at least one of the probability. And there were options. If you go to the assignment,
Okay. I have to. You can tell me the problem. I think currently if I try to,
Okay. So there was the option 2, comma 0.54 into 10 to the power 3.
hmm,
This one we we have already calculated this probability of the one two.
hmm,
And the second we find the two for the two parts. Okay? And the second one probability was 0.45 into 10 to the power 3.
hmm.
So I need to ask you the question I have asked at, find the probability of at least one of the probability. So answer will be 0.54 into 10 to the power 3. Therefore, the option was incorrect because they have given the answer 0.99 into 10 to the power 3 because they have provided the addition of 0.45 and 5.
Okay.
So
Uh,
I think it was incorrect value.
so if the most probable tree is asked, so the tree which has the highest probability, that would be the answer. If the probability of the sentence is asked, then you have to sum it up. So if you see that is not what is, if the answer is not following that, you can just drop a mail to NPTEL. And you were there in the last session as well, right? We had solved a very similar problem last time, right? Last week itself. So if you go through that as well, I think you'll, you'll be able to understand if there's been a mistake also.
Yeah, in the question actually they have asked about the at least one of the probability. So at least there will be the 0.54. Not asked about the complete probability. And during the session, when the PNR told me
Mhm.
we can take only the one probability for the single sentence. So just
Okay. Um, I'll tell you one of some of the guidelines. So if say given a sentence, it has say three probability trees. Okay, three pass trees that you can obtain. If the most if the most probable tree is asked, for each of the pass tree you compute the probability. The one which has the highest probability value, that would be your answer. However, if it is asked what is the probability of the sentence, so you need to sum up the probability values for each of the past trees that you obtain, and that would be the answer. So these are the rules these are actually rules. So if you follow this, your answer would be correct. If it is conflicting with what they have provided, you can just simply drop a mail. No problem in that. If it is fine. If
yeah,
you understand the concept that I said. If you're
yeah,
abiding
yeah.
by that, it's fine.
I know the but uh, they have asked at least one of the probability. So what is it?
But
I believe anyone answer should be good.
Yeah. According to this question, there will be quite many answer. I have mailed, but most of the persons mail them. But let's see what. And one more ma'am doubt that I have asked in the previous session with you about the null production.
mhm.
The start is correct, contains the null production or not. So you told me you are not sure about it. But in the second session with the searching document, he told us there can be, yeah, we can calculate the start state with the null production. It depends on we are considering it or not. So if we are considering, so there will be one null production. This was also incorrect. Actually, this doubt I have been asked to all PML.
Okay. Um, so I think I'm not aware what happened in the other sessions, but if you understood so we had practiced two problems, right? We took two problems last week. So if you understood that and if you followed the steps thoroughly, I think it's well enough. I don't know whether there are alternate solutions available, but if you understand one way of solving properly completely, I think it's fine. So don't have to worry further about it. Okay.
but they have used the marks.
In assignment, no? So in assignment is still also for practice, right? So you read further on that maybe. So I think just try a few more problems. You more the problems you practice, you yourself will develop an intuition. So assignment is fine. You maybe you missed one problem, but the final exam is still there, right? You'll get it correct over there. It's fine. Just try a few problems this week, maybe. You'll understand what is the thing, what is the case. Okay.
Okay, ma'am. And do you have any information about the final exam? Means there are availability of the English final year exam.
So I don't have the information actually. So I am only aware of the practice problems and all that we are discussing. So these are what have been made available to us.
It's available to everybody in the
Okay,
forum
okay.
or any WhatsApp group or something. Practice problems.
These that I'm discussing. So these has been made available to us actually. Is that what you're asking?
Yeah.
So like we who take the live sessions, we have access to it. So just so that we can discuss.
Is there any other forum or a group where these participants are discussing?
I think there's a group in the NPTEL course webpage. There's a forum or something. This course or something.
There is given the discussion forum.
That one.
Sorry, ma'am, if you have a few more minutes.
Yeah. Go on.
Noting this, when seeing that you are introducing stat symbol, that itself is considered as one of the products.
Yes. S dash to S that you're asking?
Yes.
Yes, that is considered as a production.
And we will give us in the past as question number 8. Okay, there is a readiness rules defined. We should decide that grammar itself is incorrect. Same rule repeated. For example, the category like uppercase C deriving a lower terminal C. Repeated twice.
So rule itself is repeated thrice, you're saying. C to C is there 3 times. So I mean that could be reduced to once instead of 3 you can write a single one, C to C.
So we should reduce and concentrate as the value grammar.
Yes. Yeah.
Actually, it's a single value answer actually.
Okay.
But it was not in top direct CMS because for the CMS we have required a non-terminal inside, two non-terminal and one non-terminal inside the single terminal. So I think that's the reason it was.
No, if we reduce it to one non-terminal to terminal C to the value.
Yeah, you can. So so there should be one terminal on the right hand side or two non-terminals on the right hand side. That is the rule of CMF.
No, so it's in the discussion.
Yeah, you can post. I think it's also encouraged that everyone posts posts and discusses between the participants in the discussion forum. You can try that out definitely. All right. Any other? Yeah.
Ma'am, I have a little doubt.
Yeah.
Actually, I have already asked you on the previous session. I just want to clear that. If start state implies itself, then we consider the new state. What if in the case start state considered by the another production rule? I mean, not imply itself, but implied by the another rules or rules production rules. So it and they will be considered the new start state.
Yeah, yeah, yeah. So that was the first step, right? We had discussed last time that if S is on the right hand side of any production rule, we add a new symbol S dash and we create a new production rule S dash to S to accommodate that.
Doesn't matter if it implies itself or any production.
So S to S, I don't think simply S to S is not meaningful, right? So there should be some like A to S or something, something, something like that.
Yeah, yeah, that.
Hmm. So in
In
that
that
case, huh?
case, we will consider new state, but in the another, like we have a given grammar, as implies A as B, and another value is given A implies S or
Hmm.
something B slash B. So in this case, no, no, no. Oh, sorry, sorry, sorry. S implies A, capital A, small b. Okay, not considering the S itself. And the second one is A implies S, B, slash A. So in this case, we will consider the new stuff.
If S is there on the right hand side, okay, just remember this statement. If S is there on the right hand side of any production rule, if you're if you're normalizing the grammar, changing to CNF, you have to add the S dash to S. The only thing is should be there on the right hand side. That only you need to keep in mind. Okay,
Okay, so as statistics will be present in the right hand side. In
from the
that case,
production
we
rule.
will add the
So I think we had discussed two problems. And the two problems we discussed last week, it was there. This maybe I think the live sessions are also being posted, no, on YouTube. If you just if you feel doubt at any time, you can go and revisit them sometime. So I think it would clarify your doubts as well. Okay.
actually, actually, I have read somewhere, we can consider the new statistic if as implies itself in the beginning.
Okay.
No idea about the other rules. That is
Okay. So if that is the case, follow. I mean, there. If you search on the internet, some different website would be telling you different rules. You're following something, just follow proper textbook. So proper follow prop. So for theory of computing and all those things, these things are there. Right? Follow proper textbook where if the rules are given, abide thoroughly by those. Okay, just follow one thing. Okay,
ma'am, which is the standard for this NLP?
for NLP.
Yes.
NLP, I think it's given in the course website as well. You can follow Zuravsky Zuravsky Martin. Those are good. It's given in the web page,
Yeah, yeah,
course web
yeah.
page.
Yeah. Okay, thank you.
Yeah. Okay, I think we'll conclude the session for today. Thank you everyone for joining.